Welcome to Study Loop.
In this problem, we have a real irreversible engine, not a reversible one. And we're asked some questions about what is the entropy and work and other things related and how they relate to a reversible engine. So let's start with the first question. This asks for the change of entropy of the universe. Notice whatever's going on in here in this part of the system, that's going through a cycle. And think of the Carnot cycle. And delta S for a cycle. Irreversible, reversible does not matter. Delta S for a cycle is 0. Entropy is a state function. All that matters is where you are. If you end up where you began, then delta S is 0. So all we got to worry about is what's going on with these reservoirs and the heat transfers into and out of the reservoirs. So reservoirs, meaning they don't change in temperature. So I think of these as isothermal transfers. So the first one, I'm going to be taking QH out, minus QH over TH, plus, now QC is going in, QC over TC. So that is the answer to part A. Part B, they want to know, is this greater than or equal to 0? Now, just from the second law, it tells you that it's going to be greater than 0. But let's see if we can understand a little more about that. What's happening is the following. Think about people walking around a room along the perimeter, and you tell them, you add heat by telling them to speed up. Now, they're still along the perimeter, so it's very easy to tell them to slow down. They're still around the perimeter. You've got the same order, or if you like, the same disordered state from one time to another, and you can easily get back. So the entropy change is 0 between those states, because if you like, the disorder is not changed. Now, though, irreversible processes, this QC in this particular case, it's got an added aspect to it. It's got a disorder piece to it. In addition, that's the guy who would tell people, you have the one part that says speed up. He's basically saying, now move randomly into the room. I'm giving you energy to move into the room. You tell them to slow down, you're not going to get back to that nice motion along the perimeter, that state of order or that state of disorder. You got a much more disordered state. So that's why the entropy of the universe increases, because you got this added aspect, in this case for QC. Okay, part C, they're looking for the relationship between the irreversible W and the reversible. So delta U is equal to 0. We're just looking at this part now, just the working aspect, the gas, whatever the system is here, not its interaction with the rest of the universe. This is equal to 0. It's a cycle, right? So as I talked about with delta S just a minute ago. So this is QH minus QC. This is the first law. So I get that W is equal to QH minus QC. This is true, reversible, irreversible, it does not matter. Now, I just mentioned that QC's got this added aspect. It's bigger, than if it was just reversible. So QC is greater than QC reversible. So if I were to replace this with the reversible form, this difference is going to be larger, which means the work done reversibly is going to be larger. So, and the second law tells us that also. Part D asks, is there a way, using what we have in front of us here, delta S and T, to actually get the difference between these two works? And the answer is yes. There is this quantity called the work unavailable, which talks about the degrading of energy, the inability, that you lose the ability to do the same amount of work. And that, by definition, is the difference between what you could do reversibly minus what you can do irreversibly. That's the meaning of it. So W unavailable, W reversible minus W. That's the meaning. We lose something. If we did this process reversibly, we'd gain. We'd have more work. If we do it irreversible, then we don't get as much. That's what we mean by we still have the same energy involved in all this. The energy's not changed, but it can't do as much work. It's degraded. And this, if you remember the formula, is the lowest reservoir, which in this case is TC, times delta S of the universe. That's that formula there. Okay. For the problem, we need these numbers: TH, 852 Kelvin, TC, 314 Kelvin, QH, 1285 joules, and W, 264 joules. So we need those numbers. Now, the first thing we're going to need is QC. You can see from above, that I can get QC from this. QC is equal to QH minus W, and that's going to be 1021 joules. Now for part A, they want delta S, the universe. We have the formula, minus 1285 joules, 852 Kelvin, plus 1021 joules over 314 Kelvin. This works out to be 1.74 joules per Kelvin. That seems to be changed positive, greater than 0 as we expected, or as we predicted from before. B, they want to know the work done reversibly. Now, let's go back. Here's delta S reversibly. QH, TH, QC, TC, but now this is 0. This is 0. And so that gives me and this should be marked reversibly. So that gives me the QC reversibly is TC, QH, TH, which is 314 Kelvin, 1285 joules over 852 Kelvin, and this comes out to be 474 joules. Now I can use the formula from before, W reversible, QH minus QC reversible is equal to 811 joules. And lastly, they want to know the difference. Does it work out? The TC delta S. So, and let's see this. It's going to be TC delta S of the universe. 314 Kelvin, 1.74 joules per Kelvin, and this works out to be 546 joules. You might say if you did the 811, it's 547. That's because we had around the 1.74. And that is the whole problem.